Okay, in this segment, we're going to talk about relativity and quantum theory. And the last lecture, we presented this mysterious correspondence between laws of black hole mechanics and laws of thermodynamics. Somehow, the black hole area is related to entropy, and black surface gravity is related to temperature. And so this will lead us to talk about Hawking uh, radiation, which is a quantum fluctuation around the event horizon. And so to give the proper context, we need to explain the relation between relativity and quantum mechanics, in particular something called Planck Scale, and talk about quantum field theory, and talk about quantum gravity. And uh, as for Hawking radiation, we'll first give a qualitative explanation, then present the result from quantum field theory in a curved space-time, explain what is quantum field theory in curved space-time. And then we'll try to decipher the meaning of black hole entropy. Okay? So give the proper concept between relativity and quantum mechanics, something called the Planck scale. Uh, GR, of course, is classical macroscopic theory. Okay? But for a microscopic description, we need quantum mechanics. So therefore, we need to try to unify quantum mechanics and general relativity. It's something quantum gravity theory. Turns out the natural scale of quantum gravity is Planck scale. Okay, so explain what Planck scale is. Soon after his 1900 discovery of the Planck's constant, Max Planck noted there's a self-contained system of natural units of mass, length, and time that can be defined in terms Newton's constant, which of course represents gravity, Planck's constant, of course, quantum theory, and C, of course, that's relativity. And so to do this, let me remind you the dimension of the units. Planck's constant times C has units of energy times length. And of course, also from Newton's Newtonian energy, the Newton's constant times mass square divided by length has the dimension of energy. So therefore, I can put this energy into the Planck's constant times C. So therefore, the Planck's constant, because I put it in, the length cancel here, so this has a dimension of Newton's constant times 2 power of mass. Or the 2 power of mass has a dimension of Planck's constant over Newton's constant and times C. Okay. So this allows to define a Planck's mass simply to be the square root of h bar c over Newton's constant. Now, once you know the Planck's mass, you can easily define a find Planck energy, which is the Planck's mass times c squared, and you just plug in here. Plug the number is come out to be 1.22, 10 to the 23 MeV, million electron volts. And you can also write down Planck's length, which is remember Hc. Hc has a length of energy and length. So if I divide by energy, Planck's energy, I get a length. So that's Planck length, which is 1.6 10 to the minus 34 or 35 meters. This is an incredible short distance. And Planck's time, of course, can be gotten by take the Planck's length divided by c, and gets 5.4 10 to the minus 44 seconds. Okay. So we're talking about extremely short distance time, right? 10 to the minus 44 seconds, 10 to the minus 35 meters. And also extremely high energy. To give you a sense how high the energy is, the highest energy the current accelerator, which is the LHC at CERN in Geneva, can achieve is 10 tetra electron volt, which is 10 to the 7 electron volt. Now compared to the Planck's energy, 10 to 23 MeV. So Planck's energy is 16 order magnitude higher, bigger than the highest energy we can achieve in our lab. So I'll say something about quantum field theory and also in contrast to quantum gravity. Quantum field theory is the union of special relativity with quantum mechanics. So we provide a quantum description of fields. Okay, it's the quantum field theory, and for example, quantum electrodynamics, example of quantum field theory, and the classical field, like Maxwell's electromagnetic field, is formulated in the context of special relativity. Okay, so therefore, a quantum description of the Maxwell's field, which of course is special relativity, means that's why it needs quantum field theory. The quanta of a field regards particles, and so the quantum electromagnetic field is photons. The quantum of electron field is electrons, so on and so forth. Okay, and what's remarkable is quantum theory provides a natural language to describe the interaction among matters and the radiation that includes the creation and destruction of particles. Usually, like force, you can only talk about change acceleration, but if you want to describe the creation and annihilation of particles, you must use the language of quantum field theory, which encounters special E equal to mc squared. However, the union of special relativity and the quantum does not restrict us to operate any particular energy scale. You don't have to go to quantum scale to say, for your apply quantum theory, okay, any energies will be fine. Of course, the central claim of quantum field theory is that the essence of reality is a set of fields subject to the rule of quantum mechanics and special relativity. All observed phenomena are consequences of quantum dynamics of these fields. That's okay. And of course, the crowning success of quantum field theory is the standard model of particle physics, which describes very well the strong, weak electromagnetic interaction of three of the four basic forces. Now, quantum gravity is a union of gravity, which is general relativity, with quantum mechanics. Quantum field theory is special relativity with quantum mechanics. This is the quantum description of fields, including gravitational field. Its quanta is graviton are coupled to like energy momentum 4 tensor, just as photon interact with 4 current of electromagnetic vector current. And GR with its geometric interpretation in the warp space must somehow emerge as the macroscopic limit of quantum gravity. In the same way, Maxwell's electromagnetic theory emerged from quantum electrodynamics. So that tells you how it relates to various. Now, but the natural scale of quantum gravity is a Planck scale. Okay, so it was to say when you need to use quantum gravity, you have to go to the extraordinary short distance, extraordinary high energy of Planck's energy, Planck's length. So in this context, all observed phenomena may be macroscopic. So gravity is too weak at our preferred scale to reveal its quantum nature. So it's possible we will never really need quantum gravity to describe anything we can access to in experiments. Now we'll say something about quantum field theory in a curved space-time. Okay, the surprising theoretical discovery by Stephen Hawking that a black hole can radiate, contrary to general expectation that nothing can escape from it, was made in the context of a quantum description of particle fields in the background of Schwarzschild geometry. It was it was a quantum field theory describing electrons, photons, and protons, whatever. But gravity is still treated classically. So therefore, as a background of uh, of some curved geometry. So therefore, the relevant theoretical framework involved only a partial unification of gravity and quantum mechanics. While the field of photons, electrons, etc. treat a quantized system, gravity is still described by a classical non-quantum theory of GR. Thus, the relevant theoretical framework is something called quantum field theory in curved spacetime, and quantum field theory for particles and curved space-time for gravity.